Hello, future scientists. I am Atom. Today, we are diving into the fascinating world of power. Not the kind that comes with a cape or a magic wand, though that does sound cool, but the physics of power. In physics, power is a measure of how quickly work is done. For example, a train moving slowly up a hill versus an identical train speeding up the same hill. Same amount of work is done by both trains in reaching the top, since the change in gravitational potential energy is the same in both cases. But different amounts of power are exerted by the two trains. Why? This is because power is the amount of work done in a given amount of time. The formula for power is power equals work divided by time. Uppercase P equals W over T. So work is denoted as W in joules, time is T in seconds, and power is the uppercase P in joules per second. There is another commonly used unit for power, and that is watt. 1 watt equals 1 joule per second, and you can use W as a symbol for watt as well. The unit watt is named after the legendary Scottish engineer/inventor James Watt, who lived from 1736 to 1819. James Watt is renowned for his groundbreaking improvements to the steam engine, an invention that played a crucial role in the Industrial Revolution. He was inspired by his experience with a common household item, a tea kettle. He observed the lid of a boiling kettle repeatedly lifting and dropping. This inspired him to design a separate condenser for the steam engine that greatly increased its efficiency. Watt's work led to the widespread adoption of steam power. Talking about steam engines, here is challenge question 1 for you. Train A goes straight up to the hilltop. Another identical train, B, goes up the hill on a winding track to the exact same destination. Compare the work done by both and the power exerted by both. According to work energy theorem, work done equals delta GPE. The work done remains the same for both, since both the trains changed their gravitational potential energy by the same amount. This is because they both have the same weight and they both have the exact same displacement of the same vertical height. But the power exerted differs because power is how quickly work is done. Since the straight track train A takes less time to reach the top, it is more powerful than the winding track train B. Now, let us look at another unit of power, horsepower. 1 horsepower, defined by James Watt himself, equals 746 watts. Using the term horsepower allowed James Watt to effectively communicate to potential customers who could understand the power of an engine by comparing it to the power of a horse. Ordinary car engines typically have power outputs ranging from 100 to 300 horsepower, while train engines designed for heavy hauling over long distances often boast horsepower ratings well above 4,000 horsepower. Challenge question 2. Convert 300 horsepower and 4,000 horsepower to watts. We can use dimensional analysis to do this, and the conversion factor we are going to use is 1 horsepower equals 746 watts. So 300 horsepower will be 300 horsepower multiplied by 746 watts divided by 1 horsepower. So the horsepower and horsepower would cancel out and you get 223,800 watts. And we do the same process for 4,000 horsepower and we get 4,000 horsepower equals 2,984,000 watts. Now, let us look at how power relates to velocity. So power equals work divided by time, which equals force times delta D divided by time. Now, we can write delta D over T as velocity, since velocity equals displacement divided by time. So power is equal to force times velocity. The higher the force and the higher the velocity, the greater is going to be the power. Power equals force times velocity is a fundamental concept in sports such as baseball, where combining force with the high bat velocity allows players to hit the ball stronger and further. Challenge question 3. Ion of mass 50 kilograms climbs a ladder which is 3 meters tall in 6 seconds. How much power did Ion exert climbing the ladder? Power equals work over time, which equals force times delta D over T. Here, the force is Ion's body weight, which is 500 newtons, delta D, which is a vertical height, is 3 meters, and the time is 6 seconds. Plugging in all these values, we get the power equals 250 watts. Challenge question 4. A 2000 kilograms train accelerates from 100 meter per second to 120 meter per second in 30 seconds. Calculate the power of the train. Power equals work divided by time. Work is also equal to change in kinetic energy. Here we can see the kinetic energy of the train is changing since it is accelerating from a velocity of 100 meter per second to a velocity of 120 meter per second in 30 seconds. Delta KE equals final kinetic energy minus initial kinetic energy. And we can write this as 1/2 times mass times velocity final squared minus velocity initial squared. Now we are going to plug in all of the values in here. Mass is 2000 kilogram. VF, which is a final velocity, is 120 meter per second, and VI is 100 meter per second. We get work is equal to 4,400,000 joules. Power equals work over time. So 4,400,000 joules divided by 30 seconds equals 146,667 watts. And there you have it, the physics of power. Until next time, keep exploring the wonders of science and stay curious. Happy learning. Thank you.